So, Fahim, we spent last day figuring out the directions of the forces and the directions of the fields. Today, we're going to ask, how do you calculate the magnitude? It's kind of a reverse vector. Normally, I do magnitude and then direction. We do direction and then magnitude. So, if there's a force on moving charges in a magnetic field, which there is, we know how to find the direction. How can we find the magnitude of the force? In the interests of saving a bit of time, although I'd love to do a lovely proof, I'm just going to give it to you. The magnetic force on a moving charge is Q times V times B. That V is a lowercase v, it's speed or velocity. It's not an uppercase V voltage. If it was voltage, I would have put the wings on it. This is one of the reasons I introduced that a couple of our last unit. The force on a moving charge depends on three things. How big the charge is, which kind of makes sense. How fast it's moving, because it's cutting through more magnetic field lines in a shorter amount of time, and how big the magnetic field is. Except all of these need to be perpendicular to each other, although charge is a scalar, so I don't need to put a perpendicular there. The velocity and the magnetic field need to be at right angles to each other. That's when it's at its maximum. Sometimes they're not perpendicular. They might be moving at an angle. Did I say angle? There is a component thing. It's really b sine theta, and so really it's F equals QVB sine theta. Have I told you that there is a component just now, Aiden? Say yes. I'm not going to assess you on it. I'm not going to give it to you in the homework, but it's not a big stretch if you're looking at this in post-secondary physics. Okay, ooh, I heard someone's phone. They want to make sure that's on vibrate or we're getting our Timbits. But here's what I do want you to notice. If F equals QVB sine theta, what if the field and the charge are parallel? If they're parallel to each other, what's the angle between them exactly in degrees if they're parallel? Be obvious. 0 degrees. What's the sign of 0 on your calculator? What's the sign of 0? What is it? Sine of 0 is 0. That's why this question from yesterday, I said there's not going to be any deflection. The force on that electron would be QVB sine theta, but theta is 0 degrees. If the charge and the magnetic field are parallel, no force. So charged particles move in a direction if they move perpendicular. Oh, what's the sine of 90 degrees if they're at right angles? Fahim, what's the sine of 90? And you get QVB, which is what I just told you. And that's the situation we're going to look at. So the maximum force is experienced when particles move in a direction that's perpendicular through the magnetic field. And Dean, that's what we're going to look at. So basic plug and chug. A proton, it's a proton, is moving at 1.7 times 10 to the 6 meters per second. It enters a 0.15 Tesla magnetic field. 0.15 Teslas, is that big? What did I say was really big? 1 Tesla. This is pretty big. Okay. And it's at right angles, there's our key trigger, to the field. What's the net force on the proton? So this is magnetic force, our new equation. You should also see where it is in your formula sheet. It is there. F equals QVB. Hannah, I would encourage you to stick with me here and save that for later. Thank you. Get organized later. Jaya, is the velocity and the magnetic field at right angles? Did it say it's perpendicular? Woohoo! Okay, we're good to go. Q, it's a proton. Thank you, Jeff. Thank you. You're looking on your formula sheet. It's fairly elementary to figure out the charge on a proton. That's a hint. What is it? Okay. It's often going to be protons because we often accelerate protons. V, they gave that to me. B, 0.15. How big is the force? 0.5, that's a typo, 0.15. I got 4.08 times 10 to the negative 14. I need a thumbs up or no? Got a couple of nods. It's a force. Units. Good. Victor, what's B want me to find? I should call this part A and I should call this part B. What's the next thing it wants me to find? What did I find in part A? Oh, how about F equals what? Get the A by itself. I think the acceleration is going to be the magnetic force divided by the mass. It's going to be 4.08 times 10 to the negative 14 divided by the mass. What's the mass? It's a proton. Again, thank you for cluing in. It's on your sheet somewhere. Of course, all of us are just going to go answer button divided by 1.67, Mr. Dueck, times 10 to the negative 27. Big acceleration on a proton scale. This is a massive force. Is it 2.44 times 10 to the 13th? Yes. .44 times 10 to the 13th. Mr. Dueck, what, Marcus? I remember the speed of light is 3 times 10 to the 8th. Yeah. How can we have an acceleration that big? That would mean that if the proton was accelerating for over like 1 second, starting from rest, it would be going 2.44 times 10 to the 13th meters per second because it's accelerating by that meters per second per second. Doesn't that violate special relativity? Two things. Number one, as it sped up, its mass would increase, and so its acceleration would change. We learned that in Physics 11. But actually, number two, this force is not causing the proton to speed up. It's causing it to change direction. Trust me. We're going to get to a neat application. So QVB is our first one. We use that when there's an individual charge. But if you have a wire, you know what? That's a bunch of charges holding hands. Each one of those charges will feel a force. Therefore, the wire should feel a force. If we have a wire carrying current perpendicular to an external magnetic field, it will experience a force. I showed you that little demo yesterday where we made it swing, and we saw the MIT version of it as well. The direction of the force can be calculated using the right-hand rule. This is the thumb high five. The magnitude of the force, it depends on three things. How strong the magnetic field is, which I think tend to make sense. Stronger magnetic field, bigger force. How big the current is, because that's how many charges per second. And how much wire is in the magnetic field, because more wire, more charges, each one of which is going to feel a force. We can prove it. We're going to start with our equation we just did, FB equals QV B. And then because current was defined as Q over T, Joanna, get the Q by itself, please. I can replace the Q with IT. So on the next line, I'm going to write FB equals ITV. Ooh, but not only that, as long as we're not speeding up or slowing down, if this is only causing charges to change direction, then D equals VT, which means I can replace the V with a D over T. And I get this. FB equals I times T times D over T times B. Just pick up from where we are. Ooh, Emily, what happens to the T's? It's current, I, times D, actually length of wire, times B, magnetic field, which is what I said the three things it depended on. We don't write it like this as an equation. How did I write it on your formula sheet as an equation? Find me the one that has a B and an I and an L in it. Did I write it as Bill? Did I write it as BIL, or did I write it as... It should be right next to the QVB one, I think. What did I write it as? FB equals... Anyone, I want to get it in the same order. What did I write? BIL. I did it because why would I never write a lowercase l like that? I always write it in cursive. Always write it in cursive. So I found a font to write it in cursive. Yeah. BIL. And all of these have to be at right angles with each other for that right-hand rule thing. So that's Bill. Okay. And it comes out of QVB. One there is really important. With a bit of cleverness, we can turn this into motors. A couple lessons from me. Example 4 says, find the magnetic force and the direction on the wire. So, okay. Well, Dean, what does it want me to find? Find the... Okay, magnetic force on a wire. My abbrev for magnetic force is FB, B for magnetic, and it's Bill. Do a quick check. Is the length of wire, the current, and the magnetic field, are they all at right angles with each other? Good. Then we can crunch this. How strong is the magnetic field in this question? Massive magnetic field. I don't know if you remember the MRI video I showed you yesterday was only 4, and that was destroying things. So this is 1.5 times stronger than that. What's the current? What's the length? Don't say 70. Thank you. How many newtons of force will this wire experience? Sorry? 21? Is it? Units, newtons. Ooh, they didn't just say they wanted the magnetic force. They also wanted the right-hand rule. Okay. Which way is the... try this on your own, and then I'll do it up here if you're stuck, but try it on your own first. Okay? So if I was solving this, right thumb in the direction of the current, magnetic field... Oh, you know what? I was going to bend like this. I'm just going to go stick my hand down here. Fingers in the direction of the magnetic field. Which way is my palm pointing relative to this, my piece of paper? Into the page, yes? Or if you wanted to, you could have written that. In my answer keys, because these symbols are hard to make, I always write out into the page or out of the page. But if you're looking for an abbrev, I'll figure it out. Example 5. If the force on a 5 centimeter, nice try, Dueck, 0.05 meters, piece of wire carrying 12 amps, is that, what's the magnetic field strength? Ooh, Taya, what's this wanting me to get by itself? What does it want me to find? Just read the question, you'll figure it out. Magnetic, what symbol, what letter are we using as our abbrev for magnetic field strength, folks? B. Okay, I see a wire, I see a current, I see a force. Taya, I think this is our magnetic force in a current carrying wire equation. But what do they wanted me to get by itself? Get the B by itself. How will move the I and the L over? Yeah, don't overcomplicate it. By the way, what this really means, Taya, is if you know how strong a force you want to apply to something, you can customize it by knowing the magnetic field and the current you're running through it. It's going to be the force divided by IL. You could work your way backwards and say, how strong a magnet do I need? It's going to be 1 times 10 to the negative 3 divided by 12.05. That's a typo. Did you get 0.001 and then 6 repeating? I'll go 1.67 times 10 to negative 3. Ooh, units, Taya. Magnetic field. What are the units for magnetic field? It was the new one. What was it? Tesla's. Is that a big magnetic field? Fairly big. Earth is about 100 times weaker than that. Point being, Taya, as far as I'm concerned, this equation has 4 variables. If I give you any 3, you can find the 4th. Fair enough? Calculator issue? Typo? Silly typo? Really silly typo? Yeah, okay. There's some neat applications. Some of you might recall it's a dated movie now, but there was a movie and a book came out called The Hunt for Red October. It was written by Tom Clancy, and the premise of both the book and the movie is that Russia has invented a super silent submarine, a nuclear submarine that's indetectable because it has engines with no moving parts. It uses something called magnetohydrodynamics. Here is the physics theory behind it. So this is the use of magnetic fields to propel ships. The idea is you would run a current I through seawater while seawater is passing between large magnets. How will this propel the ship? So I'm going to stand up. I'll talk louder so the microphone hears me. Those of you that are on YouTube, I'm sorry. So first of all, let's draw in the magnetic field lines. Magnetic fields always point from what to what? So do me a favor, please. Draw in a couple of magnetic field lines like that. What direction is the current flowing? That's what those X's are meant to indicate. What direction is the current flowing? What's transmitting the current? The seawater. Okay, seawater is conductive. So everybody, if you point your thumbs into the page or my screen, and which way is the magnetic field? What direction will the charged seawater molecules feel a force? Out the back like a jet engine. It's an engine with no moving parts. And because the seawater, those are the charged particles, they will go squirting out the back. It will be very quiet. You can go FB is in that direction. So there's kind of a neat application. It's not very fast, so that's why you're not going to see speedboats using that. But in the nuclear brinksmanship between Russia and the US, where it's all about having your nuclear submarines be undetectable, the whole idea behind the nuclear submarine is both the US and Russia don't know if is there a nuclear submarine parked just off of Washington or parked just off of the coast of Russia. That's one of the main reasons they're not firing their nuclear bombs. And the quieter you are, the more likely it is you can get away with. I don't know whether this has been fully developed. I saw years ago the movie and I looked up what they were talking about. The physics, at least on paper, is sound. Kind of cool. So, yeah? Yeah? Okay. Into the page, down. It's going to get pushed that way. I know, these are tricky. So we've looked at the magnetic field on a single charge, QVB, magnetic force, sorry, on a single charge, QVB. We looked at the magnetic force on a wire, Bill. How do we create magnetic fields? Well, solenoids. I showed you an example of a couple of solenoids yesterday. This is the magnetic field of a solenoid. This is really nice. This allows us to customize exactly how strong a magnetic field we want for the task at hand. A solenoid's magnetic field strength depends on several things. It depends on how many turns of wire. Every time you add a loop of wire, that increases the magnetic field. If you double the number of turns, you've made the solenoid magnetic field twice as strong. It has to do with the current. If you double the current, you've made the solenoid magnetic field twice as strong. In other words, N, the number of turns of wire, and I, the current, are going to be on top. The other thing we learned is the longer the solenoid, the weaker it is. The shorter, the more clumped together you can make those turns of wire, the better it is. So if you look up, again, sorry for those of you at home on YouTube, there's a reason why I told the kids wrap the wire around the top of the screw. There's always one kid that wants to make it nice and neat and go along the entire screw, and I have to tell them stop. We've dramatically decreased the strength. In fact, would have made your solenoid probably 3 times weaker because you tripled the length. Unwind it, cram it as much as you can around the top. So Ampere determined that the magnetic field inside a solenoid depended on certain variables. The current, bigger is better, so I is on top. The number of turns of wire, more turns is better, so N is on top. The length of the solenoid, the shorter the solenoid, the bigger the field, so L is on the bottom. In other words, he found that magnetic field was proportional to N times I divided by L. However, that will not give you Teslas. Much like we needed to multiply the gravitational equation by a big G, 6.67 times 10 to get newtons, little k, there is a constant. It may be my favorite constant because of the name. So in the latter two, for gravity, gravitational field, and for electric field, we needed to add a constant. We need to do the same thing for magnetic field. So magnetic field of a solenoid, B, if you want to, you can put a little SOL, is equal to mu with a 0, N times I over L. We pronounce that mu naught because the Brits named it. 0 in Britain is naught, N-A-U-G-H-T. So mu naught times N times I over L. What is mu naught? It's on your formula sheet. Probably right below the K, I'm going to guess, or at least in the same area as the K and the big G. Joanna, what is it? Sorry, what? For what? What the heck? Pi? Really? Pi shows up in weird locations. The universe really seems to like that number. 4 pi times what? Has the best name. What's it called? The permeability of free space. What did you learn in school today, Joanna? Mummy, I learned that the permeability of free space is 4 pi times 10 to the negative 7. Oh, Joanna, you are ever so clever. What are its units? I can figure it out. It would be Tesla meters divided by amps, I think. That's what it has to be so that you get an answer in Teslas. Unfortunately, this is going to be a problem. Some of you will not be able to type 4 pi scientific notation button -7. You'll get an error. If you get an error, what you'll need to type is pi times 4 scientific notation button. The TIs should be okay. I think the Casios, you're going to get an error. And I don't know why. For some reason, Casio doesn't treat pi as a number. And so it doesn't think that it can go in front of scientific notation. So your workaround will just be go pi times 4, scientific notation, -7. Weird. There's a second version of this equation. This is used much more in industry. Sometimes all you know is the ratio between the number of turns of wire and how long the solenoid is. In other words, sometimes all you know is the number of turns per meter, the number of turns of wire per meter. This we use a lowercase n as our abbrev for. And so you can also find the magnetic field from a solenoid from mu naught, Mr. Dueck. I was going to write out 4 pi, but we have an abbrev for that, Mr. Dueck. Mu naught. And then what is it? Did I write I times n or did I write n times little n times I? What did I put on your formula sheet? Which one, Joanna? Little n times I, like that? Okay. When to use that one? It'll be pretty obvious, and we won't use it much. I'm doing it because it's used in industry. If you're ordering solenoids, they're going to be graded as the number of turns per meter. They're not going to tell you how long it is. So let's crunch some numbers with this. A solenoid is carrying 4.2 amps. If the solenoid is 1.2 centimeters, Victor, nice try. 0.012 meters long, and is made up of 750 turns of wire. By the way, 750 turns and 1.2 centimeters. Yeah, you can get solenoids that are that dense. They're expensive, but you can get them. What's the magnetic field at its center? Victor, what's this asking me to find? What is the of A? I'm looking for where that starts the letter S and has an oid at the end. Okay, so it wants us to find the solenoid. Well, that's going to be mu naught N times I over L. Victor, what was mu naught? 4 pi times 10 to the negative 7. What's N, the number of turns of wire? Yep. I L 0.012. How many Teslas will the magnetic field at the center of this solenoid be? By the way, an MRI machine is basically one massive mother of a solenoid, and you're lying in the middle of it. That's why they're shaped like a, I was going to say, like a tube. That's why they're shaped like a solenoid. What'd you get? And all of you want to try typing this in to see if you get that weird error or not. Especially if you have a Casio. I don't know if the Sharp handles it or not. The TI, I know I can go clear. 4 pi scientific notation negative 7 times 750 times 4.2 divided by 0.012. Pause the video for a second. What do I get? Did you get 0.3? I guess 0.33 if I round off properly. What if I wanted to double the magnetic field? Easy. Double the current or twice as many coils. This gives us a completely customizable, however many Teslas you want, I can customize if I'm a solenoid manufacturing company. Oh, what's your amperage source? Okay, how much room do you have to fit the solenoid in? Okay, I know how many turns of wire I need to put on there in order to give you what you need. Oh, you got more room? I don't need to put as many turns of wire. Okay, great. I got all sorts of options. 0.33 Teslas. So this was my rant yesterday when I said solenoids have thousands and I crossed it out millions. They're used all over the place. A customizable magnetic field, huge advantage. Example 8 says, find the field and direction at the center of the coil. We're looking down a solenoid like it's a telescope. Okay? I didn't draw the whole body and I tried. It just cluttered up the diagram. So we're looking down the solenoid like a telescope. Which way is the current moving? I guess counterclockwise. That's what those arrows are indicating. It says the coil is carrying 10 amps of current and has 2,550 coils per meter. Let's do the magnitude of the magnetic field first. So the magnitude is going to be mu naught. Now, did they give me the current, Kyle? Yeah. Did they tell me the length of the solenoid? No. Did they tell me the number of coils? No. Instead, they told me the number of coils per meter. This is that second industry varied one where it's going to be little n times I, and little n is coils or turns or winds per meter. So it's going to end up being 4 pi times 10 to the negative 7, 2,550 times 10. We'll do the direction next, but let's get the magnitude. What'd you get for a magnitude, Kyle? At point 0.032. Give it to you the 3 sig figs. So 0.0320 Teslas. Direction. So now you imagine holding the solenoid. I guess the only way that I could hold the solenoid and curl my fingers in the direction of the current would be if using my screen, I'd have to hold my hand like this. Now my fingers curl in the direction of the current. Is the North Pole, you know what? Is this magnetic field coming out of the page towards us, or is it going into the page away from us? Out of the page. The North Pole is coming. You know what? We would say this. It's coming out of the page towards us. There's our direction. I'll change colors so it stands out a bit because the black and black doesn't look as good. Make it red. The magnetic field in the center of that solenoid is coming out of the page towards us. Putting everything together. Right-hand rules, solenoids, magnetic fields. One more. A solenoid is to be wound on a cardboard form 30 centimeters. Nice try, Dueck. 0.03. No, not 0.03, Mr. Dueck. 0.3 meters long. How many turns of wire are needed to produce a magnetic field of 6.28 times 10 to negative 3 Teslas if the maximum allowable current is 5 amps? So this would be, you're a company, you have 0.3 meters to fit the solenoid in. You need a magnetic field of 6.28 times 10 to negative 3, and just the way you're setting it up, you got a 5 amp source. Eliana, what's this asking me to find? How many what? Loud and proud, you're right. How many turns of wire? Which variable was turns of wire in my magnetic field for a solenoid equation? I'll give you a hint. Which variable was the number of turns of wire? Get the n by itself, please. You know what? Since this is the first lesson, in our notes, let's write down the originals so we know what the heck we did. In your homework, if you went straight to getting the n by itself, I'd be fine with it. What was it, Mr. Duke? It was n times I over L. Is that right? I'm going from memory here. So good. Let's get the n by itself. N is going to be, oh, and it's mu naught, Mr. Duke, not mu. It's mu naught, not mu. Oh, okay. Times by L, divide by mu naught and I. Yes? Okay. N is going to be 6.28 times 10 to the negative 3. L 0.3. Mu, 4 pi times 10 to the negative 7. I 5. Let me know what you get, Eliane. I tried to make this work out evenly. I think you'll end up having to round off a tiny bit, but I think you're going to get an answer like 0.999, or like it's going to be really close to working out evenly. I kind of contrived the numbers a little bit because when you're dealing with pi, it's usually yucky decimals. But thumbs up. What'd you get? I have no idea what you're saying. Sorry. 299.8? Isn't it 300? I was aiming for 300. Yeah. And the units for turns of wire, go figure, is turns of wire. It's just a number. So much like both of the force equations, in this equation, there are 4 variables. If I give you any 3, I expect to be able to get the fourth by itself. that okay, Taya? Yeah, yeah. What's your homework? 1 is good. 2 is good. In number 2, we have balanced gravity and magnetic forces. In other words, Fg is going to be equal to Fb. That's going to be your starting point. Fg is going to be mg because you're on Earth. You don't need to go cosmic. And Fb will be Bill. So you'll have mg equals Bill, and it wants you to find the magnetic field. Let me see. I think I'm going to skip 3. 4, I'll put a star next to it. I haven't done one this tricky yet. Your hint is do a free body diagram on the wire. Gravity down, tension up, and magnetic force is either going to be up or down. And it's all not accelerating, so it's balanced. So A is 0. Get the tension by itself. 5 is good. 6 is good. 7 is good. 8 is good. 9 is good. 11. Sorry, I skipped 9. 7, 8, 10, 11. The 12 is good. You can skip 13, 14, and 15, but you can do 16. Yeah, I know.